Good morning, student. I'm still teacher Betty, continuing with the organometallic chemistry, lesson 5. In lesson 4, we ended with a few examples of metallic carbonyl. In this lesson, we are going to continue with the more examples of metallic carbonyl. And the first one is the dianyl carbonyl preparation. It is made by irradiation of iron pentacarbonyl with ultraviolet light. When iron pentacarbonyl is dissolved in its own volume of glacial acetic acid, the solution obtained cooled and then irradiated for 6 hours. Golden crystals of dianyl carbonyl are precipitated and are obtained by filtration. Properties. Dianyl carbonyl forms crystals which are diamagnetic, slightly soluble in alcohol and acetone, insoluble in water, benzene, and other organic solvents. The crystals are non-volatile. When you look at action with heat or action of heat, when warmed at 50 degrees Celsius, it gives the triion dodecarbonyl, and at 100 degrees Celsius, it decomposes to give iron, carbon monoxide, and some iron pentacarbonyl. The structure is bridged. It has 3 bridges and 6 terminal carbonyl. Another example of metallic carbonyl is the dicobalt octacarbonyl, and the preparation is prepared by the reaction between carbon monoxide and reduced metallic cobalt at 220 degrees and 250 atmospheric pressure. So cobalt plus carbon monoxide at 250 atmospheric pressure and 220 degrees Celsius, we obtain the dicobalt octacarbonyl. It can also be prepared by the reaction of dry carbon monoxide at 200 degrees and 200 atmospheric pressure in the presence of metallic copper on certain binary compounds of cobalt, such as cobalt sulfide and others. So cobalt sulfide plus carbon monoxide plus copper, we obtain our dicobalt octacarbonyl. Then can also be obtained by the action of carbon monoxide and hydrogen on cobalt carbonate under high pressure and higher temperatures. Cobalt carbonate plus hydrogen plus carbon monoxide at 120 to 220 degrees Celsius and between 250 to 300 atmospheric pressure, we obtain the dicobalt octacarbonyl. It can also be obtained by the action of an acid on a solution of cobalt tetracarbonyl. Hydrogen is involved in the reaction and the dicobalt octacarbonyl is left. Properties. Dicobalt octacarbonyl is an orange-brown crystalline substance. which melt with a melting point of 51 degrees Celsius. It is soluble in alcohol, ether, and tetrachloromethane. It is sensitive to air in both solid and aqueous or in a solution state or states. It is thermally decomposed at 50 degrees Celsius in an inert environment, in an inert atmosphere, to give a tetra-cobalt dodecacarbonyl. Action with air. On exposure to air, dicobalt octacarbonyl is converted into deep violet basic carbonate of cobalt. Reduction reaction. It is reduced to cobalt hydride by hydrogen at 165 degrees Celsius and 120 atmospheric pressure. So dicobalt octacarbonyl plus hydrogen at 120 atmospheric pressure and 165 degrees Celsius, we get the cobalt hydride. It is also reduced by sodium metal in liquid ammonia below temperatures below 75 degrees Celsius negative or in tetrahydrofuran. Reaction with halogens. Halogens decomposes dicobalt octacarbonyl according to the following reaction, where we react the dicobalt octacarbonyl with a halide to give the hydride of cobalt and the carbon monoxide. The structure. There are two structures observed. In the solid state, the dicobalt octacarbonyl exists as a bridged compound. We have two bridges and the 6 terminal carbonyls. And in liquid state, it exists, it only exists as non-bridged structure with only terminal carbonyls. Other examples of metallic carbonyls are nickel, palladium, and platinum. For these three, it has been observed that nickel tetracarbonyl exists, while palladium tetracarbonyl and platinum tetracarbonyl do not exist. There are mainly two factors which explain the non-existence of carbonyls of platinum and palladium. And those two factors are the spin promotion energy and the ionization energy. So in the structure of the metal tetracarbonyl, where M stands for nickel, palladium, and platinum, the metal atom is in sp3 hybridized. In order to get the vacant sp3 hybridized orbitals, the N(s)2 electrons must be promoted to N-1 d8 orbitals so that N(s)2 N-1 d8 configuration becomes Ns0 N-1 d10 configuration, spin pairing configuration. So for the promotion of the N2s electrons to N-1 d8 orbit, energy is required. And this energy is referred to as the spin pairing promotion energy. This spin pairing promotion energy of nickel has been observed that is less than that for palladium and platinum. And this means that nickel changes its configuration from the 3d8 Ns2 to 3d10 Nso more easily than the palladium and platinum. and hence nickel tetracarbonyl is easier to form. In other words, we can say that nickel tetracarbonyl is formed while the palladium tetracarbonyl and platinum tetracarbonyl are not formed due to having high spin pairing promotion energy during their formation. Another factor can be explained as follows. It has been observed that one of the electrons from the 3d10 orbitals of nickel atom to pi antibonding vacant orbital of carbon monoxide less energy, called the ionization energy, is required. Less ionization energy is required than that which is required for the transfer of one electron from the 4d10 or 5d10 orbitals of palladium and platinum to the pi vacant orbital in the carbon monoxide molecule. When we compare the energy, nickel has got 4.5 electron voltage, while palladium and platinum have got 8.2 electron voltage. So that is the energy required to transfer electron from the 3D for nickel to the pi vacant orbitals of carbon monoxide, and also for palladium and platinum from the 4D or 5D, the energy is high. This indicates that the d-electronic change of nickel atom can be transferred to the pi antibonding orbital of carbon monoxide more easily than the d-electronic charge of platinum and palladium. And that is the higher energy accounts for the non-existence of palladium and platinum tetracarbonyl, while the low ionization energy required to transfer the d electrons to the vacant pi orbital for nickel is less, which accounts for its existence. Nickel tetracarbonyl. Preparation. It is made by passing carbon monoxide over finely divided metallic nickel at a temperature below 100 degrees Celsius. So nickel plus carbon monoxide gives rise to the formation of nickel tetracarbonyl. Nickel tetracarbonyl can also be obtained when carbon monoxide is passed through an alkaline suspension of nickel cyanide or nickel sulfide. So nickel cyanide plus carbon monoxide is equal to nickel tetracarbonyl, or nickel sulfide plus carbon monoxide gives rise to the nickel tetracarbonyl. It can also be prepared by disproportionation of univalent nickel. On reduction of potassium tetracyanonicorate 2 with the potassium amalgam, a ready solution is obtained. This potassium tricyanonichrate may be isolated, and this compound, when absorbed, this compound absorbs carbon monoxide at 90 degrees Celsius. It results into the formation of a compound. On treating the solution of this compound with hydrochloric acid, nickel tetracarbonyl is obtained. Properties. Nickel tetracarbonyl is a colorless liquid boiling at 43 degrees Celsius and solidifies at -25 degrees Celsius. It is miscible with benzene and insoluble in water. Nickel carbonyl is highly poisonous, and it reacts with the sulfuric acid to produce nickel sulfate. So nickel tetracarbonyl plus sulfuric acid, it gives rise to the formation of nickel sulfate plus hydrogen and carbon monoxide. Action with nitrogen monoxide, slightly moist nitric oxide. Nitric oxide react with nickel tetracarbonyl in a gaseous state or in a solution in a chloroform to give a compound of intense blue color. The equation is given below. There is a point to note here. When a nickel tetracarbonyl react with nitrogen monoxide in the absence of water, a blue solution of the composition is obtained, of this composition is obtained. Substitution reaction. Carbon monoxide groups can be replaced by nitrogen dioxide or by phosphorus trichloride and organic compound. Action with the heat. Nickel tetracarbonyl, when heated to 180 degrees, gives nickel. In a pure state, nickel carbonyl explodes to form nickel, carbon dioxide, and carbon, as can be seen in the equation. The point to note here is that under higher atmospheric pressure, say about 100 atmosphere, it is, however, known to decompose even up to 250 degrees. Oxidation reaction. A solution of this carbonyl in organic solvent is readily oxidized by air, developing a pale green gelatinous precipitate. And the gaseous hydrogen chloride decomposes the solution of nickel tetracarbonyl involving hydrogen and carbon monoxide. So nickel tetracarbonyl plus hydrochloric acid will give rise to the nickel chloride, hydrogen, and carbon monoxide. Reduction reaction. When a nickel tetracarbonyl solution in tetrahydrofuran is reduced by sodium or potassium or magnesium amalgam, the carbonyl tetranicolate is formed. While with lithium, nickel tetracarbonyl gives rise to lithium trinickel octacarbonyl. Uses. Since nickel tetracarbonyl is decomposed to metallic nickel, it is used in the production of nickel. It is also used in gas plating and also as a catalyst. The structure of nickel tetracarbonyl is tetrahedral with only terminal carbonyls. Now let us look at the effective atomic number. What is effective atomic number? Is the total number of electrons surrounding the coordinated metal ion in metal carbonyl, including those gained from the metal ligand. An explanation is as follows. After the ligand have donated a certain number of electrons to the central metal ion through metal ligand bonding, the total number of electrons on the central metal atom, including those gained from the ligand in the bonding, is called the effective atomic number. The total number of electrons surrounding the coordinated metal ion is equal to the atomic number of inert gas, which follows the central metal atom in the periodic table. This is called the effective atomic number, LOL. When the EAN is 36 for krypton, 54 for hexanon, and 86 for radon, the rule is said to be followed or obeyed. How do we calculate the effective atomic number of metal in metallic carbonyl? The following rules must be observed. The central metal atom, we have to remember, the central metal atom is in zero oxidation state, and hence the total number of electrons in the central metal atom is equal to its atomic number. You remember, atomic number is equal to the number of protons is equal to the number of electrons. So if the metal is in zero oxidation state, therefore the total number of electrons are equivalent to the atomic number of that atom. Each of the terminal carbonyl group donates 2 electrons to the metal with which the group is attached. And each of the bridging carbonyl group donates only 1 electron to the metal atom. Each of the metal-metal bonds donates 1 electron to each of the metal atom. Let us have an activity. Calculate the EAN of the following metal carbonyl. Number 1 is the nickel tetracarbonyl. This carbonyl has a tetrahedral structure. I showed you this, in which the nickel is attached to 4 terminal carbonyls. 1, 2, 3, 4 terminal carbonyls. Therefore, the EAN of the nickel carbon is equal to the atomic number of the nickel atom plus the electrons donated by the 4 terminal carbonyls, by these 4 terminal carbonyls. And remember, the rule said each terminal carbonyl provides 2 electrons. So this is equal to 28, 2 times 4, since there are 4 terminal carbonyl groups, then 2 times 4 is 8 plus 28. The answer is 36. Therefore, the rule is obeyed, since this is the atomic number of the inert gas. Number 2, the dianion carbonyl. In this carbonyl, each ion atom is attached to 3 terminal carbonyl group. Each ion is attached to 3 terminal, 1, 2, 3, this ion, and also 1, 2, 3, this side. And the 3 bridged ketonic carbonyl groups, this is 1, 2, 3 bridged, and 1 metal ion, 1 ion bond. So we have this ion and this ion, we have only 1 bond. So the EA of ion atom is equal to atomic number of ion plus the electrons donated by 3 terminal carbonyls, 1, 2, 3, plus electrons donated by 3 bridging carbonyls. We have 1, 2, 3 bridging carbonyl, and electrons donated by 1 1 ion bond. So 1 ion bond each contributes a half, and we get 1 electron. Each contributes an electron to form a bond. This is equal to 26 plus 3 times 2, 1, 2, 3 terminal carbonyl, and each contributing 2, plus 3 times 1. We have 1, 2, 3 bridged carbonyl, each contributing 1 electron, plus 1 times 1, 1 bond, 1 electron being contributed by 1 ion, 1 metal, and the total will be 26 plus 6 plus 3 plus 1 is equal to 36. This is the atomic number of inert gas. Therefore, the rule is obeyed. As an assignment, I can leave you with: draw the structure of the triion dodecacarbonyl and calculate its EAN. Confirm whether it obeys confirm whether it obeys the rule or not. This has marked the end of the organometallic unit, also the course of the bioinorganic and organometallic has come to the end. I wish you success, and I'm still Teacher Betty.